Good afternoon and welcome to the instrument making live stream session for the Galactic Center Star Party. This is our very first ever instrument making live stream, so we hope you enjoy what you're going to see. Before we begin, I'd like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connection to land, sea and community. We pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. This afternoon, we're bringing you our fourth stream of 7, so we're at the halfway mark right now. We have ASV Instrument Making Section Director Mark Justice and a few of his team from Instrument Making Section that'll be joining us. As always, a bit of housekeeping. Raffle tickets, we've got less than 180 tickets left now. It'll be drawn tonight at the start of our Deep Sky live stream session at about 9 o'clock. So if you haven't got them, you've got to grab them now or you won't get a chance to. For those of you on YouTube, you can donate stickers. We had someone donate their first sticker on YouTube in the last live stream, so that was a bit exciting. And on Facebook, you can donate stars. So it all goes towards our All Abilities Astronomy project, which ASV Section Director Mark Justice will tell us all about towards the end of this live stream. He was going to give us a presentation on that telescope. With all the formalities out of the way, it's time to bring Mark and his team in. Good afternoon, Mark.
Hello, everyone. Hello, Mark. Thank you. Welcome, everyone, to this stream. I'm Mark Justice. As you know, I'm the section director for the instrument making section. And a week and a bit ago, Mark asked me whether we could try and put together a bit of a live stream for him. And I went around the team and asked a few people who are from instrument making, and people were pretty keen. So tonight we've got 5 presentations. Note that we're doing the presentations, but please feel free to ask questions and Mark will fit them in amongst the talk or between talks or at the end of each one, whatever he seems suitable. So please ask questions, and they don't have to be on the topics we're talking about. You can chuck some stuff left of field if you like. So we've got 5 people presenting today. We've got Rod Breckenridge starting up. He's talking about his telescope making and why he makes telescopes. Then we'll be followed by Barry Adcock talking about a collection of unusual telescopes. And then we've got Stuart Beveridge who will be talking about the building of his clamshell type backyard observatory. And then Jim Starkey will be talking about adding setting circle capability to his Dobsonian telescope. And then to finish up, I'll talk a little bit about the telescope part of the ASV's All Abilities Astronomy project. So yeah, so that's it. So Rod, are you ready to start the show rolling?
Yes, I am.
Okay, over to you, Rod.
Hello, everyone. It's great to be here this afternoon. I wanted to talk to you a bit about my telescopes and a bit about why I build them. There's a photo in front of you of 2 scopes I've built. A 12-inch telescope is the larger one, and an 8-inch one is the smaller one. I got into telescope making probably when I was a child, teenager really, back in the 70s. And at that time, telescopes were extremely expensive. I think in dollar amounts, they're probably about the same now as what they were back in the 70s. But of course, cost of living was quite different back then to what it is now. So it was really beyond my ability to pay for as a child. So I got into making my own instruments back then. And I got to know an elderly gentleman who had actually made his own telescopes. I used to visit him once a week and spend some time with him, and he'd help me learn how to build things because I was absolutely hopeless with tools at the time. And I learned a lot from him, just watching him nut out how to do things. I think I probably learnt more from how he went about thinking about problems than the actual skills. Over a few months, probably a year or two actually, I built a 6-inch F10 telescope, and I had a lot of fun with it. And a few years later, I built this scope you can see in the picture here. It's a 6-inch F5, and At the time, I made it with a cardboard tube and a simple chipboard or plywood mount, and I used that for several years and enjoyed it. And a few years ago, I decided to improve it a little bit, and you can see the octagonal wooden tube there now, which I enjoyed building. One of the things that I like about making my own telescopes is I can actually make them in a way that actually suits the way I observe. And if you have a look at this 8-inch telescope here, you can see a couple of features on it that are perhaps different to a commercial instrument you might buy. One is it's got a Telrad finder. Most of the commercial ones I've seen have an optical finder, which personally I find a little bit hard to use. I prefer a Telrad. It sits on an equatorial platform, so I can actually track with it. And it has a little degree circle at the bottom, and Jim's going to talk a bit more about those later on, and that enables me to find objects. And near the handle on the top of the scope, you can see a little metal plate, and that's where I can place an inclinometer to help me find things in the sky. I actually built this with my son several years ago, and it was a great kind of project for us to do together. And one of the things I've found over the years is involving my children in building or decorating telescopes has been one way in which I've actually been able to get them into the hobby. And my son still enjoys coming away with me now to Heathcote when we get the chance. He's 22, and it's something we look forward to doing together from time to time. Now, I actually make my own mirrors, and I really enjoy doing that. And mirror making's a bit of a dark art, I think, to many people, but it's an interesting one, and it's had a bit of a resurgence. I think for a few years there, we weren't seeing many people wanting to make mirrors at instrument making, but in the last few years, we've had a lot of people come along saying they want to give it a go. And I've got a photo here of 2 of our younger members getting involved and making and grinding their own mirrors. And we've had 3 teenagers in the last year or 2 get really involved in mirror making, and well on the way in one case to making a good instrument, and 2 others who have finished some really good instruments as well. For people who do come along and want to get along in making their own mirror, we can also help them with the whole process. In the previous slide, you might have seen some barrels and the 2 young guys trying to make a mirror as they walked around a barrel, and that's the traditional way of doing it, and there's nothing wrong with that. But Mark and I have made 2 turntables that we can actually loan to members that just make the process a little bit easier. One of the things I did last year during the lockdown was I decided, after spending a whole lot of time walking around barrels and standing over motorized turntables, that I'd actually like to motorize the whole process of making a mirror. And I built my own machine, and there's a photo of it there. It took me a few weeks to make, and I had a lot of help from Mark in particular, and quite a few other members from the instrument making section gave me some advice on what to do. And here's a picture of it in action, just polishing a mirror. And I've been finding that I'm getting really good results with this machine, and it was actually quite a lot of fun to make. And it's just made again out of wood. It's all plywood, form ply that you get at Bunnings. And it has some DC motors that enabled me to run it. You might have noticed earlier that I use some octagonal tubes on some of my telescopes. Use these with smaller scopes. I find they're a really nice way to set up my instruments. They're relatively easy to build. I'll show you how I do that in a moment. I think they look quite nice. You can make them out of a relatively thin plywood. I use a 6mm ply to build them. And they give you a nice set of flat surfaces. So you've got a flat surface on the top for your finder, and in my case for the inclinometer, you can see in the middle. The focuser sits at a roughly 45-degree angle, and you don't need a tube box like you do with a round tube. the altitude bearings can go directly on the side of the tube, and that makes the whole instrument just a little bit smaller and a little bit lighter. So I quite like building instruments this way if I can. And I think one of the other nice things about making things out of wood and doing them like that is they become a bit of a talking point when you're at a star party. And I quite enjoy talking to members of the public about how they've been built. And it seems to be quite an interesting topic to many people. Here's a little short video showing how I cut the sides of the octagonal box. And you can see the bevel down the side there. And I'm using a router bit with a 22.5-degree angle on it. It's sitting on a router table, but you can actually just run a router along a board that's bolted against a vertical piece of timber that's clamped down. So I actually commonly now do this process on a large table saw, which is a little bit easier for me. But it's not that hard to do. And if anybody here wants to make their own tube for a telescope, I'm certainly happy to help and cut the pieces for them. Putting it together goes actually fairly easily. We've done this in instrument making a couple of times where we've helped members make their own octagonal tubes. I'll just show you how it's done. I'm just using a polyurethane glue there to seal up the edges, and then I clamp it together with some tape and a pipe clamp. With a taller tube, I'll use a few more pipe clamps, like is shown here. So I've just finished making a smaller tube for a smaller telescope I'll talk about in a moment, and that's the tube you saw being made before. I think it's come up all right, looks okay. And there it is next to the 8-inch one that you've seen earlier. Now, I wanted to say a couple of things about my 12-inch telescope, just as a bit of a lesson, I suppose, for people. You can see a truss tube version of it on one side of the screen there. It's actually motorized. It has a full go-to capability in that format. So I could control that with my phone. I could control it with the little PC you see attached to the telescope. A late friend of mine, Jeff Dudley, is there. He helped me a lot with the electronic side of that particular telescope, and I had quite a bit of fun with it. But what I found over a few years of using that scope was that I spent so much time actually setting the thing up, aligning it, and sort of dealing with some of the bugs involved in travel, moving a scope that had a lot of complexity with it from home to a dark sky site. I'd often find a wire would snap or something would go wrong, and I'd spend a couple of hours in the evening trying to fix everything before I could actually observe. So a few years later, I actually bit the bullet and I just simplified the whole thing. And on the other side, you can see a round wooden tube I made and a much more simple Dobsonian mount with degree circles on the bottom. And I've actually got a large equatorial platform I can use with that telescope if I choose to. And what I've found over the years is I don't really need tracking when I go to a dark sky site. I prefer just to be able to find things and look at them in a wide field eyepiece. And I use platforms more when I'm actually doing public demos where members of the public might be wanting to look through the eyepiece. And I've got a row of people who want to look one after the other at Saturn or Jupiter or something like that. And the equatorial platform saves me from having to move the scope between observers. So people often ask me why I build my own scopes, because the commercial ones are relatively cheap and you can get some pretty good value instruments for not too much money. I think one really good reason for making your own is that you can develop the skills to make a better telescope in many cases, something that suits your needs a bit better than perhaps what you can buy commercially. You can certainly make them a lot lighter. The commercial ones are quite heavy from my experience, and they're bulkier than they need to be. But another really good reason is so that you can actually build something that perhaps you can't buy commercially. As you develop skills from building, say, a modest 6 to 8 inch telescope with a moderate focal length, you can then start looking at something a bit faster, or if you like Barry, you might want something a lot slower with a long focal length. And shown here is an instrument that perhaps looks pretty ordinary, but it's actually got an f2.7 mirror. That's a mirror that has a focal length of about 27 inches for a 10-inch mirror. So it's a very fast telescope. It's built by Mel Bartels, who's a very well-known amateur in the US, who sort of pushes the boundaries on telescope making and makes really interesting instruments. And after building a number of smaller ones, he actually built this. Is actually a 25-inch telescope with an f2.6 mirror. So as far as I know, that's probably the fastest large telescope you'll find anywhere, at least in amateur circles. And it's a 25-inch mirror that requires no ladder. And that's a picture of his wife, I think, standing next to it. So you can get an idea of the proportions. It's actually quite a portable, very large telescope. So if he hadn't been an amateur developing his skills over the years, he certainly wouldn't have been able to do that. There's quite a few new technologies coming on board at the moment that are enabling us to do more and more. You know, we're all aware of 3D printing and how Arduino boards make things easier with electronics. And some of this stuff is helping us to build things like equatorial platforms a bit more easily, or to build the testers that we want for testing mirrors a little bit easier. You can actually download files now for 3D printed versions of bath interferometers, which we can use to test mirrors very accurately. So there's a lot of interesting changes that are making our hobby a little bit more innovative and a little bit more able to develop instruments that just probably weren't possible a few years back. One of the things that people like Mel do, and this is one of his mirrors, is they're actually casting their own blanks. So you can see here that that's actually a 30-inch blank for a telescope he's just finished. I think he's making 2 of those that size. His intention is to make a binocular telescope with those, and yeah, he cast these two mirror blanks, and I know he's finished both of them and he's testing them at the moment. So yeah, interesting kind of instruments he's building. Now, I always thought really fast telescopes like f3, f2.5 and so on were really just out of reach. And I remember Logan, who was very active in our club a couple of years ago, he built his own 10-inch, I think it was f6 mirror, and he did a really good job on that. And I remember talking to him, and he said to me, he said, "What do you think I should do next? I'd really like to make another one." And I tried to encourage him to make something easy, something like a long focus Newtonian. And he said, "Oh, no." He said, "I'd like to try something a bit harder than that." So he chose to make a 6-inch f3 telescope, which I was really worried would be too hard and would put him off the hobby altogether. He actually finished it. There's a picture of him there with it, and he did a great job. I've looked through it once, and the star images on it were good, and you know, nice pinpoint images. Yeah, so you know, he really did a great job with that. So I decided to make my own fast mirror, and the tube you saw earlier is the tube that goes with it. It's an 8-inch f3, and here's a picture of the tester that I used to verify that it was finished. It's called an autocollimation test. You can see a big flat mirror on one image in front of a sort of a very jury-rigged telescope. And what happens is that you look at the image of a light source reflected through a grating that is then reflected, sent out to the flat mirror, reflected back into the telescope, and you see the lines that you've got on the other side of the slide. Now, straight lines in this case indicate a parabolic mirror. A parabola is what we actually need for the telescope to work properly. And those straight lines there indicate that this is a finished mirror. So I was quite pleased that I was able to do that. So it's quite a challenge to make mirrors this fast. So you might be thinking, why would you bother making such a fast mirror? Well, there's a few reasons which are probably obvious. And if you look at that photo there, I think they show them. The smaller telescope there actually has a bigger mirror than the one next to it. So the smaller looking telescope was built by Mike Lockwood. He's a very famous mirror maker in the US and makes very high quality mirrors. And that's f2.5 or f2.6, and it's got a 14.5-inch mirror. And the other instrument next to it has a 12-inch mirror, and it's f8.6. Now, I don't want to cast any doubt that the 12-inch mirror is probably excellent. It'd probably be fantastic for looking at planets and looking at the moon and things like that. But its disadvantages are obviously its size and some of the issues that come with the size and the need to get up a ladder to get to the eyepiece. The 14-inch f2.5, on the other hand, is very, very portable. So they're the sorts of advantages you get. You're also able to see more nebulosity, and you can obviously have a much wider field of view with the fast telescope. The cons, of course, are that you're going to need a much larger diagonal than what you might otherwise. So mirrors like this are usually going to need a diagonal of about 30 to 35% of the size of the primary mirror. So really keen planetary observers may not like that terribly much. Collimation needs to be absolutely excellent, so you need to have very good cells made for the secondary mirror and the primary mirror. All that's doable. It just takes a little bit of work. And telescopes like this also require wide field eyepieces to really take advantage of what they've got to offer, and a coma corrector. And you're thinking about things like Naglers or Explorer Scientific, and they're fairly expensive pieces of equipment to buy. So, whereas with a slower Newtonian or a long focus instrument, you can get away with less expensive eyepieces. That's not the case with a fast mirror. So if you want to build your own telescope, I guess you might be thinking, what's the first step? Well, the first thing would be to maybe get involved in the instrument making section, hopefully when these lockdowns are finally over. Decide whether you want to buy a mirror or whether you want to just modify a telescope, or whether you want to actually make your own, and do a bit of research. There's actually some fantastic websites available, and some good online interactive boards that you can get involved in, like Ice in Space or Cloudy Nights from America. Go to Mel Bartel's site and have a look through there. There's an enormous amount of information on telescope making. But please bear our section in mind, because we'd love to help you and give you whatever assistance we can. And I'll hand back to Mark.
Okay, Rod, thank you very much. I enjoyed that. Do we have any questions for Rod, Mark? Or
we've got a couple of comments. Well, one's a question that's been answered in the chat, and Rod just also answered it then. And it's how do we sign up for making our own telescope? And well, Rod answered it. Join the ASV's instrument making section, and in order to do that, you have to join the society. And the easiest way to do that is go to www.asv.org.au/join. Become an ASV member, and you can join the instrument making section as well as a lot of our other sections. And Robert was just noting that one day he'll have a go at making a telescope at his local men's shed. Not sure on making a mirror there. Well, Robert, become an ASV member again. Come and join the instrument making team, and they can help you make a mirror. So a lot of people, looks like they enjoyed it, and people keen to make telescopes. So as you said, the easiest way to do that is become a member and have a chat to Mark and Rod and the guys at Instrument Making section.
Yeah. Once you're an ASV member, you're automatically part of all the sections. So you join ASV and then you're straight away welcome to join into instrument making. I mean, obviously at present, they're not in person, but we are still conducting Zoom instrument making meetings. We tend to have a presentation or two, and then you would be welcome to ask questions, or you would maybe prep me beforehand and I'll prep a few people and try and get some answers for you to be discussed online. So even with lockdown, and we're still doing instrument making via Zoom. It's not nearly as good for us because it's hands-on, but it still gets your interest, answers a few questions. So please feel free to join in. We might move on. Thank you very much, Rod. Mark, any other questions, or we'll move on?
Robert said he's already a member, so he just needs to make contact with you via the members section on the website.
Yeah, please do. Please do, Robert.
Same with Giridhar, who said he's just signed up for membership. So
excellent.
Giridhar should get in contact with you as well through the ASV members website under the members section.
Yeah. And there is an instrument making Facebook page, and we do have an email list that I can prod you if you prefer to stay in touch that way. But just email me or phone me to start with, and I'll point you in the right direction. Okay. Well, thank you, everyone. The next presenter is Barry Adcock, who's going to talk about a collection of unusual telescopes. As you can see there, I'll say over to you, Barry. You ready to go? Okay.
Yep. Thank you, Mark. Now I'm stuck already, Mark. How do I start? Can you start it, or?
No, you'll have to start the slideshow. We can roll through from there if you're having trouble. You can just do it this way if that's going to be a bit easier for you. Everyone.
Yep, Barry, you can just step down through the slides in that view if you wish.
Yeah.
I can't.
Or you can't. Click on the left panel on the various slides. You click on the second one down from the top. Do you get the next one? On the preview of slides on the left, can you advance down?
Yeah.
Click on that one. It doesn't work. Hang
on, I've got a different.
I think
just take your time, Barry.
You might need to Alt tab across. There we go. I think we got it. Maybe. There we go.
Excellent. Excellent.
Yep.
All yours, Barry.
Well, good afternoon, everyone. Like Rod, I made a telescope as a youngster. It was a 5-inch F10 telescope, and it was at a time when telescopes in shops did not exist. There was no such thing as Bintel or any other optics outlet. So the catchphrase at the time was, if you wanted a telescope, you make it yourself or you go without. And that's really the one of the primary aims of the instrument making section, is that we make things ourselves. Now, at about that time, I became interested in looking at the planets and other solar system objects, and I tried to work out how I could improve the images that I was able to get. Probably the first reaction to that is to get a bigger telescope, but when you got 2 shillings a week pocket money and there was nowhere to buy them anyway, it wasn't an option. So I decided that to improve, looking at details on the moon and the planets is all to do with resolving power, not so much to do with light gathering power, but the telescope has to have a decent resolving power. And there are 3 things we can do to improve the resolving power of a telescope. Now, I don't want to get very technical, and we'll just look at this first couple of slides. If we look at a star with a perfect telescope, we don't see a tiny pinpoint image of light. We see a disk, and that disk is called the airy disk. And that's surrounded by a series of rings called diffraction rings. And it turns out that that's because of the nature of light. We can't do anything about it. That's what we get. and 83% of the light that we're gathering ends up in the airy disk. The other 17% is in the diffraction rings, and that's for a perfect telescope. If we do some horrible things to the telescope, like putting a central obstruction in front of it, we alter the diffraction pattern, and you can see from this little diagram here that as you change the size of the central obstruction, the effect is to take light out of the airy disk and place it into the rings. And that doesn't do anything to help the resolving power of the telescope. In fact, it makes it a lot worse. Then we can make things even worse again by putting in a spider support for the secondary mirror. And that again reduces the resolving power. Now, this resolving power, we can just look at that in terms of a single diagram. That's a double star where the two stars are the same magnitude. And if we see them something like that, then we say that the stars are resolved. And that has a direct relationship to detail on the surface of planets. I should mention also that we can make those airy disks smaller by making the telescope bigger. So increasing the resolving power, we get a bigger telescope, and we do any of those three things that I've just mentioned. The second thing is to make the telescope long. Perhaps not quite that long. That was made in the 1640s by a guy called Johannes Havalis in Poland. And it was, well, put it this way, if you watch the footy on television like I do, you'll know what 50 metres is. And that telescope was 50 metres long. I often wonder what these people were doing here, whether they were wanting to have a look through it or whether they're all gathered there to help move the telescope. But things progressed from there on. He made that telescope also to overcome the problem of chromatic aberration. The third thing we can do to improve the resolving power of the telescope, sorry, that's the focal length, we make it longer. The longer the focal length provides a bigger image size, and use of a Barlow lens may not be necessary if we're going to image the planet. The sensitivity in figuring is proportional to the focal length squared. So if we're going to make our telescope, if we make a 6-inch S5, as Rod mentioned several times, we have a certain sensitivity in the tests. If we make a 6-inch F10 telescope, twice as long, then the sensitivity of the tests is 4 times greater, not 2 times. And also this applies to the alignment as well, so that we get a greater sensitivity in aligning the telescope if it has a long focal length. The third problem that we can confront is atmospheric turbulence. And turbulence occurs in the atmosphere above the telescope. Turbulence also occurs within the telescope structure, and things like the mirror, the tube itself, and even the observer can muck up the turbulence. And a telescope with a closed tube, such as a refractor or a Cassegrain reflector or a Masseter telescope, will help the turbulence in the telescope. So if we take into account those three objectives, we can do something about increasing the resolving power of our telescope. That led me into an area of telescopes called tilted component telescopes. They can have mirrors or lenses or both, and they can be short focal lengths or long focal lengths, but they all have one thing in common. They get rid of the central obstruction. And if we have a look at a classical Cassegrain telescope, which I have people are familiar with, we have a primary parabolic mirror and a secondary convex hyperbolic mirror, not easy to make, and that produces a Cassegrain telescope. If we take that secondary mirror and push it off to one side so it's no longer in the road, and we tilt it at the same time, we produce probably the simplest form of tilted component telescope, and that's called a Schiefspiegler. Schiefspiegler is a German word, and it means oblique reflector. And the Schiefspiegler is simply a Cassegrain telescope. It has a primary mirror and a secondary mirror, which can be spherical, tilted, and it produces an image at an angle to the incoming light. And as I said, it has no central obstruction, and it goes some way towards increasing the resolving power of the telescope. Over the years, I spent quite some time making prototypes and experimental Schiefspieglers, and I'll just show a picture of a couple of them. That's a picture of a tiny Schiefspiegler. The primary mirror is tucked away inside the box. That's a similar box, a similar little box of what Rod makes for his telescopes. The secondary mirror is up at the top of there, and the light from the sky comes down, misses the secondary mirror altogether, reflects at an angle up to the secondary, the primary mirror altogether. It misses the secondary and then is reflected down to the eyepiece. That's a picture of another little Schiefspiegler telescope, and if we put the two together, that's the one I showed in the other slide. There are two different sorts that one can make. By tilting the primary and the secondary, we introduce coma and astigmatism, and we can eliminate one or the other, but not quite both. So the telescope on the left is a telescope for reducing, compensating for coma. The one on the right compensates for astigmatism. The next telescope I made is on the top of a tripod, is a 4-inch or 100mm Schiefspiegler, and I used that over the years for an enormous number of times. I used it to, I set it up for looking at the sun and the planets and moon, and we take it along to star parties and look through it. And people always, when we look at the moon, people say, oh, that's not looking at the moon at all, because this tube here doesn't really point at the moon. It's the little one that points at the moon, and it does really look quite odd. Following that, I actually made a large Schiefspiegler. That's a picture of my observatory. That dome is made of fiberglass panels that I molded in the backyard, and that's the big 350mm Schiefspiegler, and what you're looking at there is the end of the secondary mirror, which almost sticks out through the dome, but it doesn't quite. As a telescope, it really doesn't fit very well at all in the observatory. It's just too big. But anyway, that's the secondary mirror cell that you can see at the top there, and the actual surface is pointing downwards. That's a very poor picture. Inside the observatory, it's just impossible to take a picture of the whole thing at once. But up at the end here is the primary mirror cell, made of aluminium. The basic telescope is made of timber, and that's the secondary slow motion drive, which is also made of a timber gear. The secondary is off there to the left where you can't see it, and it reflects the light down to the eyepiece at the where I'm pointing to there. It has two finders. One is at the bottom, and the other one is at the top of the telescope where we can't see it. In 2017, my wife and I went for an overseas holiday, and we timed it to go to a tilted component telescope convention that was held in Beveridge in Germany, and I've just got a couple of pictures to show you. The Schiefspiegler itself was popularized in the 1950s by a guy called Anton Kutter, and that's his telescope. He has died since then, but it has been restored, and that's also a 12-inch Schiefspiegler. He used that telescope to make an atlas of the moon, and he wrote a book called Gleanings Bulletin A about Schiefspieglers, and that was published in Sky and Telescope in around about 1957, I think. But another telescope in the convention had show you how complicated light can become. The primary mirror again is at the bottom of that tube. Light would come along, be missing everything, be reflected at an angle up to the secondary, and then there'd be a tertiary mirror inside the box, and it would come out to the side of the telescope, and that's called a Trischießspiegler. I notice I've only got a few minutes left, but I do have another unusual telescope to show you. It is an 8-inch refractor. It's F30, and it has a focal length of, if you convert that in meters, it has into metric dimensions, it has a focal length of 6 meters. That's a very long telescope, of course, but this particular telescope is mounted so that the light is fed from what we call a cytostat mirror. And under that structure there is a 300 millimeter optical flat, and that receives light from the sky. When those doors are open, of course, it reflects light down a path which is parallel to the Earth's axis of rotation. And under the floor there, under the ground, I should say, is a second optical flat. Just where my arrow is pointing there is the 8-inch objective lens, and from the second flat, it reflects it into an underground room where I can sit down and look through the telescope. That's a picture of the cytostat mounting. It rotates just like an ordinary telescope on a polar axis every 24 hours. That's a picture of the secondary optical flat underground with the covers taken off. There's a few plants around the place to convince you of where ground level is. And that's a picture of the output of the telescope in my underground room. And that's the focusing mechanism. There's the eyepiece there, and that's a focusing wheel. So that's all I had to present, Mark. It's all about unusual telescopes.
Okay, thank you, Barry. Fantastic stuff. Some of it I've seen before, but there's some interesting stuff, and always great to see some of it again. Thank you, Barry.
I'll tell you what, Mark.
Do we have any?
We've got a question.
Sorry.
But I've never seen an underground house, an underground telescope before. It's impressive.
He's hiding it from his wife.
Oh, reckon.
No.
Barry, did you design?
I
Did you design that specifically so it looks like a heating unit outside a house, so that she thought it might have been a heating unit and not a telescope?
Oh, my kids used to call it the dumpster. But
The dumpster. Yeah.
if we can go back to the
yeah, you can go back to the slide if you want to, by all means. If you can get it back there. While you do that, we do have a question on the
that hood comes down. It just looks like a council dumpster that's out in the street.
Doesn't look like a telescope. Pretty tricky.
Yeah.
Very impressive. There you go. Like Neil's saying, I love the idea of being able to sit inside the house looking through an eyepiece that never moves.
Yeah. It is comfortable in the winter time, but one of the big advantages is if I go out at some odd time of the night, it doesn't wake up the dogs of the neighbourhood.
Well, there you go. That's true. I just wake the possums up with the coffee grinder when it moves from star to star, from object to object. They go scurrying along the fence. Now, we do have a question for you. Lee wants to know, does the Schießspiegler suffer from ambient light entering the tube from there being 2 entry points for light? I was actually wondering the same thing.
It can. It's got to be very carefully baffled. Cassegrain telescopes have baffles inside them so that when you look through the eyepiece end, you don't see any of the sky. And a Schießspiegler has to be carefully baffled. It is possible to do that. And if it is properly baffled, then there is no problem with stray light.
Hopefully that answers your question. Rod Westwood is saying that he's looked through the Stellarphane Schießspiegler, and what a version of a Schießspiegler it is. I just like saying that word. That's a nice word to say.
Yeah. Oblique reflector.
Oblique reflector. No, let's go Schießspiegler. It sounds so much better.
Yeah.
That's all we've got on those ones, Mark. So we could probably jump across to Stuart's presentation, is it?
Yeah. So the next presentation will be by Stuart Beveridge, and he'll be talking about the build of his observatory. So it looks like you're ready to go there, Stuart. Over to you.
Yep, you can hear me.
Yes, we can.
Thank you for asking me to present this today, Mark. So
My
I
pleasure.
think it's been said by both Barry and Rod that the disadvantage of Newtonians is having tube currents and temperature control, and it's very difficult to do that when you're hauling the telescope from a warm temperature inside and then hauling them outside to look at the planets. And Mark and myself do planetary photography, and so what we were having to do all the time, and Mark still does that, is to get the telescope outside fairly early and turn fans on and try and get the temperature of the optics to the same temperature as the ambient outside air. And one advantage of having an observatory is that you don't have to do that. I just go out to my observatory now, turn on the fan about an hour and a half before I plan my observing session, and go back inside. So anyway, I shall make a start. So now, Mark, how do I progress this?
Your slideshow is ready to rock. You need to Alt-Tab across to your slideshow so you can start.
Right,
yep.
Right, okay.
You won't be able to see us, but we'll be able to see you.
How's that?
Looks good.
Yep.
So back in the 2019 or 2018, it might have been, I had an opportunity to review my friend Cliff Ashcraft's presentation regarding his 3 observatories. He lives in New Jersey, and the first design caught my eye, and I thought, I think I should be able to build that fairly easily and fit it into my backyard. So in 2018, I was at the Vic South Star Party and sent this photo to my wife of my friend Gavin and myself, suggesting how well this observatory would look in my backyard for a mere $6,000, to which I had no reply for some time. And eventually, when the reply came through, it was a suggestion of "and pigs might fly." So I promptly forgot about that idea. And then also in 2018, I had a big tree that was causing me a lot of grief in my yard fall over, clearing the way and in my yard to put an observatory, and started me thinking again. So in previous trials, I tried a shower tent over my, I use an equatorial platform that you can see there with the rollerblade wheels and the electronics and mechanical items on the right. I tried a shower tent out for a while, but after a few nights, it just doesn't protect the telescope well enough, and I decided that it was okay short term, but long term, I definitely needed to go with something else. So back to planning, I looked again at Cliff's design, and I just decided that his first observatory would fit in my yard in the designated and approved spot, but would it suit my needs? Would it fit my gear into it? And was it big enough? And Cliff approved me to go on and borrow that design. So it's quite clever in that it's designed to use standard 8-foot by 4-foot sheets of plywood, which is roughly 1200 by 2400 if you go to Bunnings, and it simplifies the building of it. So I went ahead, and the original plans were to use 4x4-inch posts, but I decided to go with a 90 by 45. And if I needed to use one as a beam, I'd just use a builder's trick and bolt 2 together. So I laid out some wood on the ground and put my table and my telescope there, and I decided that the floor space was good enough, and that I could also stand up inside. And because I've seen other designs of people who make these type of observatories and they end up crawling into them, and I didn't want to do that, so I decided that this design would work. So I built the frame and continuously checked whilst I was building it that I still had enough room for myself and the telescope without being too close to the telescope to cause hot air currents passing at the end of the tube while sitting down with my laptop imaging. And then, in case I ever wanted to move the structure, I ended up using some footings known as foundation blocks, which I bought from Bunnings. They were rated at quite a lot of weight and are designed for what's known as a floating deck. So I kept track of my progress by printing out the plans from Cliff's PowerPoint and making some scribbles and notes. And to help keep peace at my house, in parallel, I built my wife a gazebo and was able to get help from my older son, who'd been a builder's labourer in the past, which was very, very handy. So the next step after completing the floor framing was to level it onto the foundation blocks. And one reason why I chose the 90 by 45 structural pine is because the foundation blocks are actually designed for that type of for that size for floating decks. So then after I finished the floor, I went on to the ends. The rear wall is fairly straightforward, but the door end is a bit tricky. So this work was completed in my garage and taken outside in sections as I completed each one. So then both ends were bolted onto the floor and held in place by clamps. And I then bolted the sidewall top frame sections on and threw a tarp over the lot so that I could intermittently work on it in between showers of rain, which seemed to increase more when I actually had a chance to work on it than when I didn't have a chance to work on it, of course. And that idea seemed to work well for me. So once I got the frame up, the next step was to get my 8 by 4 foot sheets and bolt them onto the sides. I also had to make decisions about the flooring. So I made sure that my floor joists stuck to the 450mm rule, and I was able to use common flooring, which is otherwise known as yellow tongue. But then I realised I'd made a bit of a boo-boo and the equatorial platform didn't quite fit into the hole. So this was addressed with a triangular baseboard with 3 feet that would go on the concrete blocks under the observatory. You can see that there. So I continued to fit the walls and did a preliminary positional testing of everything before building the pivoting roof sections. I did this at night to make sure that I could see the planets, which was my primary reason for the location of the observatory. The roof frames were started on trusses, then moved into place on the roof for completion. And at the same time, I also undercoated the walls. The roof simply pivots on bolts that go through the extended upper wall frames. This has the advantage of allowing overlap on the roof sheets without the roof edges jamming into the sidewalls. So I thought that was quite a clever design of Cliff's, and he included it on his other observatories, which were the same design, so that as the roof lifts out, it also lifts away from the structure. The ridge capping I bought had to be bent to 90 degrees and cut, so I did that on my fence railings, and you can see it there as I was testing it just on the left here to make sure it was going to fit. The roof section ropes were then measured and added. Then the ridge capping was bolted to one side only. So part of this design that makes it keeps things simple is you just have ropes connected to each side, and it seems to work really well. I've never had to change it. And you can see here the overlap on the side of the roof that I was talking about before. So this was the inside view. So on the left-hand side, the left-hand side of the roof always has to open first, and then the right-hand side of the roof opens second, and then packing it away is the reverse. Then it was time to make a door. So I made that door using some wood that I had left over from a previous project and fitted it up, and worked out quite well for me in the end. The reason the door is this shape is so that when you open the door, as I said at the beginning of my presentation, you don't have to duck to get into the door, because in the middle of the night, once you leave obstructions there, you forget to duck and all sorts of bad things happen. You can drop stuff, etc., etc. So with various bits of hardware were then added to the door. Everything was undercoated, and the roof capping on the right-hand side can be seen on this right-hand image as not secured, but it actually just sits there and it works out quite well. So the floor worked out well in the end, and my triangular mount stays clear of the floor. The reason you do it that way is so that you can walk around inside the observatory, and the telescope is not actually connected to the floor, and so it stops the telescope from vibrating if you have to move, which I do in my case, because I have to quite often do platform rewinding. So my 12-inch Dobsonian, which is a 12-inch f5 on my EQ platforms, fits pretty snugly. And the observatory ended up looking pretty good in the yard without seeming out of place, because it doesn't look like Mount Palomar with a dome. None of my neighbours have said anything about it. In fact, I'm sure that none of the neighbours even know that it is an observatory. So yeah, you just, in its completed state, you unhook the door, walk in, open the left-hand side of the roof first, then the right, and you're ready to go. I've also added a solar light. You can see the little solar panel there, and there's a light inside, which turns out pretty handy when I'm shuffling around. So the whole project probably cost me, including the paint, around $1,200. Once it was up for a few months, I realised I was getting some leaks in the corners where the pivot points were. So I went through my collection of offcuts and made up these covers for each corner. And once I painted them up, they don't look out of place. And I was very lucky that totally solved my leakage problem. So now we're up to questions.
Okay.
We've
Thank
got
you,
one
Stuart.
question. We've got one
go
question
ahead, Mark.
from Rod. Rod, you can ask your question. You put it. I saw you put it in the chat, in the private chat.
Yeah, I really like Stuart's design. The only thing that's ever worried me about it is, do you ever have any problems with wind lifting up the sides when it's open?
I don't usually use it if it's windy, because it blows my telescope around anyway. But I have used it in minor gusts of wind, and no, not really, because the sides are actually quite heavy and held in tension with the rope, so they're not balanced. Now, when some people build these designs, they actually put weights on the end so that it's quite well balanced to open and shut the roof a lot easier. But because mine's so small, I don't need to do that. So it's actually under a fair bit of tension on the ropes.
Okay.
Do you have anything to lock the roof closed, Stuart, or again just gravity?
I do have a catch that I was going to add to it to make sure that the roof never flung open. But so
Yeah.
far, I haven't got around to adding that catch, and it's never moved.
Okay.
So it seems to, once you shut the roofs tight and the ridge capping is over both halves, it seems to hold it very securely.
Okay. Very
So
good.
we've got a couple of people wondering if the tree just happened to fall over, or if it had a helping hand.
I have had that question asked of me more than once, but well, I was actually away on holiday when you could travel back in the times when you could do that. And my daughter rang up and said, "Dad, the big tree in the backyard just fell over." And I thought, oh, I had visions of the fence being down and the tree landing in the next door neighbour's kitchen. And it was really, really lucky. It just blew straight over very squarely. And no, I had nothing to do with its demise.
So I've got a couple here for you. Lee wants to know, the 3 triangular posts secured to the cement blocks or just placed on them? They seem to be on an angle. Is there no slippage? Your little concrete blocks.
I presume, is that for the central mount?
Yeah.
Yeah, no. I tried to level the post as much as I could, and each leg is actually slightly longer, and there's some adjustable feet on each leg. But I did have a bit of a problem with it shaking, so I've had to reinforce the legs since I started to use it. And no, it never ever moves on the concrete blocks. It's very stable.
So Brenton wants to know, loves it. Ask a question though, professional curiosity. I know why Brenton's asking. It's the same reason I'm asking. I would ask is, I may have missed it, but any council or building approval requirements, Brenton, I reckon it's because it's under 10 square meters or 9 square meters. You shouldn't you shouldn't need a permit out where you are, Stuart.
No, it's about the same size of a fairly
It's like
standard
just a
shed that you can buy.
Yeah.
Shed that you can build at Bunnings, and I mean, there's nothing stopping you from buying a shed from Bunnings and making the roof removable.
Wow, you should still talk to council, but probably just check that one with council just to make sure, Stuart. I would. And the query, you went softwood. Why not a hardwood? Any termite protection?
I used treated pine on the floor and on all the pieces going into the into the footings.
So now the other one is, could you securely leave the scope in the observatory?
Yeah,
so
I do.
You leave your telescope out there, so it's in there.
Yep, and I padlock. I've got a padlock and a hasp on the door.
Okay, there we go.
No one's ever tried to break into it, and I've never had any visitors like from possums or anything like that try to get in through the floor. Not so
anyway.
far anyway.
No,
Had a few spiders every now and then. That's about the limit.
Spray them out. I think we're up to Jim's, are we now, Mark? Jim's presentation.
Okay. Yeah. Sorry, I missed that. Okay, the next person presenting will be Jim Starkey, who's going to talk about seconding circles on his telescope. But this is a Dobsonian type telescope. So go ahead, please, Jim.
Thank you, Mark, and good afternoon, everybody who's watching. The subject of my discussion has already been mentioned, and I guess the first question is just to ask for any who may not be so familiar with telescopes and setting circles is what they're all about. And the simple answer is simply to point the telescope to what you want to see. And it's obviously especially useful if you're looking for faint objects, which you can't see with the naked eye anyway. And even if you're looking for a 4th or 5th magnitude star, which you possibly can see, but you don't know exactly which one it is. So I'm sure many amateur observers have struggled trying to locate objects, and a lot of time is often spent doing so. Typically, if you plan to observe a number of things in the evening, you'll have a list of objects to look at, This is a typical list taken from a recent Crux magazine. And for each of the, in this case, stars that you want to look at, you get a position given as the right ascension and declination, which is generally not a great help if you've got an Azimuth mounted telescope. And what you always traditionally have had to do in my younger days is to go to the star chart and look for the right ascension and declination and thereby locate the star on the star chart and then try and observe visible stars nearby and where it is relative to the visible stars and point your telescope there to find what you're looking for. And many will attest that this is a often tedious and frustrating operation and can be very time consuming. So basically I'm addressing this talk to people who have an Azimuth mounted telescope without the go-to capability, something which would look similar to this in concept anyway. And the idea now is that the position of the stars or whatever you want to look at, we can now obtain the Azimuth coordinates from all the smart devices that we now have. And just to clarify for anyone not familiar with these concepts, the pointing of the telescope we set by, first of all, specifying the direction, or the azimuth as it's called, as an angle measured clockwise from north, 0 to 360 degrees, about the vertical axis, which we call the azimuth axis, and the tilt of the telescope upwards from the horizon towards the vertical, which we call the altitude setting, and hence the name Azimuth coordinates. So, as I say, it's those people that I have in mind in presenting this talk. I'll just go to a full screen presentation at this stage. Let me move on. Okay, so all I can do is show you an example of how this can be done on, in this case, my own very old homemade telescope, but I assume that those interested would have the necessary workshop and technical skills to implement something similar on their own telescope if they don't have such a thing. What we require is an altitude measuring scale to measure the altitude angle. And as an example, what I did first of all, I built this little pendulum-based altitude indicator. It consists of a simple steel rod with a pointer at the end, and it's suspended from a pin. It hangs like a pendulum, and if you place a scale behind it, which I did there, that can give you an indication. I've got a more detailed view of that. Just before I move on, while I've got this photograph up, I just want to indicate that another almost essential requirement of a telescope with setting circles, you have to align it quite precisely in terms of getting the base level so the azimuth axis points perpendicularly up. And that means leveling the base. And that is much more conveniently done if one has a couple of screw adjusting leveling adjustments on the scope. In my case, there's a fixed point here where you put a block underneath. Obviously, while you're viewing, you take it off the wheels and you put a block under these two screws, and then you can adjust them and very quickly and easily level the base. So that was what that was all about. Just quickly, this is the altitude scale which I built. And it turns out the problem with this is that when you adjusted the altitude of the telescope, this thing swings like a pendulum, and it takes about 10 or 20 seconds to settle, which is most inconvenient. So what I did, I built another scale here. It's got a Dobsonian mount, similar to the one that Rod described earlier. And in this case, there's a fixed pointer here. And what I can do, once this thing is settled, I can take the reading there, adjust this to correspond to that reading, and then the elevation angle, the altitude, is automatically and easily read off this scale. And while I've got this photograph up, just another convenient feature which you'd want to include is a little light to illuminate that during observation. Now I've got a little LED, which is not so easy to see in this picture, but that is a useful feature of the design. But as, again, Rod mentioned it earlier, I think it was Rod, in fact, you don't even need a circle now for the altitude measurement, because you can just fit a little inclinometer, and Rod showed one in his telescope. This is perhaps a closer up view of the instrument. It's got simply 3 buttons, one to turn it on and off, one to zero it, and one to turn on the backlight. So it's a very convenient, compact thing. It cost me, I think it was about $18 or something, not all that much. It's got a magnetic base, so you can put it on a little metal steel plate on the telescope. And you can use it to level the telescope when you're setting it up as well. You just lift it off here and put it on the base. So for most people, I think this would definitely be the way to set up a altitude indication on your telescope. This one had a claimed accuracy of 0.1 of a degree and a resolution of half of that. And that's more than adequate for what I intended to achieve. The Azimuth scale is a little more difficult. That's this big circle around here. Again, I made up my own thing, which I'll show in a moment. Obviously, the scale is fixed to the base here. And there are 2 things to note here. The one, it's also got the LED here, which shines on it. This thing folds in when I pack it away. And also the pointer in mine has got an adjustment range here. So you can correctly zero, as it were, the azimuth conveniently just by sliding the pointer instead of having to move the whole base to some exact level. If you get the base near enough, then you can just do the final adjustment on some sort of fine adjustment. This is the altitude scale. I just drew it up with a simple drawing package, and printed it out and laminated it and just put it on the telescope behind a Perspex screen. That worked perfectly well. And the azimuth scale is the same in concept. The problem in this case was that the scale is fairly big. It's about 520 millimeters across. I think there are not many people who've got a printer that can handle that at home. But I went into Officeworks, and they were happy to print that out for me and laminate it, which was convenient. I then just glued the completed azimuth scale onto a 3mm MDF sheet to make a sturdy disc, which I attached to the telescope. Setting up the telescope, I guess what I want to say is that normally a Dobsonian telescope, such as the ones we've been looking at, has the great advantage that you can probably store it in your garage and you can just carry it out and put it down on the drive or wherever you observe from, and you can start observing right away. It's not a big deal and it's very convenient. But once you put setting circles on it, then unfortunately you do need to put a little more effort into setting up the telescope. But it's not too hard. Basically, without going through all this in detail, you need to level the base, which you can do by means of the spirit level or the inclinometer, which is happily sitting on your scope for the altitude scale reading, or a spirit level, or if you've got a pendulum plumb line or something, you can use that. I think individuals can devise a suitable means to do it. Aligning the azimuth is a little more complicated. What I do and what I think makes sense is using a compass. You can usually position the telescope on the base so it's reading 0 on the azimuth scale, and then you point the telescope as close as you can to north. I've got to be able to do that with a little compass within 3 or 4 degrees, and that's a good start. If you do that, then the first thing you can do when you start observing is point to a known star or planet or the moon, preferably something which is fairly low in altitude, and center it in the field of view of the telescope, and then go to what I'm going to describe in a moment, one of the planetarium programs which are available on all sorts of smart devices, and find out what the real azimuth is of that particular star or planet or the moon, and you do a final adjustment of the pointer on the azimuth scale to get it properly aligned. So it's not that hard, and it typically takes about 10 minutes if you go to a fair amount of effort to level the thing and get everything set up. Now, to get the altazimuth coordinates of something you want to view, we talk about using one of the planetarium type programs which are now widely available on your smart device, be it a phone or a laptop or an iPad or a tablet or whatever else you use nowadays. I think these programs are widely available on all of them. There are various programs available. The one that seems to be more commonly used by our colleagues in the ASV is Starry Night. We noticed earlier, was it Rod, or one of them was using Stellarium, and I've used Ghost Sky Watch running on an iPad. But generally, I find Stellarium is a very good program. I got a version without charge. I think it was a free one. It works very well for me. And that allows you to find the altazimuth coordinates of anything which you choose to observe. Obviously, these programs need, in addition to what you want to observe, to be able to get the altazimuth coordinates, the program needs to know exactly where you are on the Earth's surface and what the time is. Now, most of these smart devices we talk about have got a GPS capability, and from that they can get both those bits of information. So it's usually quite easy, and the position on the Earth's surface you only need to enter once in the program, and it will usually restart with that information stored. And of course, the time is also maintained in these devices. So the Stellarium program, whatever you're using, it picks up that information without having to bother you at all. Now, I was going to switch to Stellarium to illustrate this if there's time, but I think I'll move on first. I'll just show you a typical slide, which is a screenshot from Stellarium. I entered in a request to search for Omega Centauri. It comes back and it shows you Omega Centauri in the sky, and you can see where it is. And traditionally, I always used to locate it by looking at 3 stars, which don't even seem familiar here. But that's not of interest. What's of interest is that when it selects that object, it gives you, amongst a whole lot of other stuff if you want it, the azimuth and the altitude coordinates. The azimuth in this case is 238.6 degrees, and the altitude is 59.3. And you simply need to set your telescope to those values, and all being well, you'll find that certainly in the finder, and preferably in the field of view, at least of a low power eyepiece. So it's a fairly simple procedure once one gets used to it, and for me, it has saved an enormous amount of time searching around for unfamiliar objects, and especially dim objects which you can't see with the naked eye. Omega Centauri, they always say you can, but I find even that in the Melbourne sky is hard to locate when there's so much light pollution. So how good is it? I've done some measurements. I think this is a second set I'll give. That previous slide, I think, was a little optimistic. I seem to have got virtually no errors. This is more realistic of some readings I took a short while ago. I looked at Jupiter and Saturn and Mars over a period of some few hours and a few stars. And for each of them, what I did, I selected it in the telescope, actually, and I centered it in the field of view of the telescope. And then I immediately wrote down the coordinates from the computer that I was using. And once I'd written them down, and then went back to the telescope and read out the azimuth and the altitude from the setting circles which were mounted on the telescope. So this is the theoretical value from the computer, these two, azimuth and altitude. And these two are the readings on the telescope, which should be identical, of course. Now, the difference is the errors which I've got here. And this gives you some idea of the precision which I achieved in the setting circles. Now, there's all sorts of rooms for small errors in setting up these setting circles and using them. And that sure is the case. You can see in many cases I've got an error of about, let me go back a step. I read these out to 1/4 of a degree. So all of them, except one, I don't know why, I forgot to round it off. They all rounded off to 1/4 of a degree. And the errors accordingly are typically plus or minus 1/4 of a degree. This one was 1/2 a degree. This one was 3/4. And this one was 3/4. And obviously that's not a very great precision, but it's enormously helpful and much better than none at all. Just a couple of comments. This one I can only say was an error because of some slight misread. And that can happen, of course, if you make a small mistake in one of the readings you do. But there's another factor that comes into play when you look at these errors. This one, for example, of Beta Theta, that star was at an elevation 46, no, sorry, it's this one that was bad, at an elevation of 70 degrees. And it turns out when you're looking at something near the zenith, the azimuth error can look very big, but it amounts to a much smaller angle in real terms. In other words, this 1.25 degrees in azimuth corresponds to something much less if you measure the great circle distance error on the celestial sphere. So overall, this performance is not that bad. It's certainly enough to be extremely useful, but I do expect that some of you making a similar thing with a properly equipped metalworking machine lab and so on could produce setting circles far more accurate. But these are certainly accurate enough, I think, to prove an enormous assistance in searching for objects which are hard to find. In most cases, I've claimed that it's better than 0.5 degrees. That certainly is usually the case. My telescope, the low power eyepiece, has got a field of view of about 0.75 degrees. So in most cases, once I've pointed it using the setting circles, the object is in the field of view of my low power eyepiece. And in every case, it's well within the finder at least. So it's been a great success for me, and it's saved me a great deal of time searching for objects by referring to charts. Now, if there's enough time left, I would like to just briefly...
How are we going, Mark?
Are we going
I think
a bit late?
we're about an hour and a half at the moment, so I think we might need to sort of
to finish it off.
Yeah.
I was going to just run Stellarium, but I think I've made the point. So I think
it's fine as it is.
Yeah. Can I just
Jim.
quickly ask Jim, is this something that we could get a template of to put on the ASV website for others to be able to download and try themselves at home? Your system you're talking
about
there?
the setting circles.
Yeah.
I'd be happy to do that, but I just want to make the point that there are many such things available if you just Google it on the web, of course. But I'll certainly be happy to put those drawings up if anyone's interested to.
I think you'd have a few people
use them.
who would be interested. Yeah, I do. Yeah. Absolutely.
Yeah, I'll certainly be happy to do that. And as I say, the process of mounting them, like everything else nowadays, there's an enormous amount of stuff on the web about this sort of thing, which people could go to. So thank you all for the opportunity to make this contribution.
Thank you, Jim. Thank you very much. Any questions there, Mark? Or we move along a bit?
Beat star hopping. So people just saying that at least that way they don't have to go from one star to another star just to find an object. That's the sort of thing that would help them.
Rod runs this on his scope, and I've been at Heathcote and he's demonstrated it working, and it works absolutely brilliantly, and it's well worth the effort to get it set up. And I think, as Jim was saying, there are websites that will allow you to create, I think, the circles. But anyway, we can come back to that. But maybe we do a little bit of instrument making.
Within the society, if we've got someone within this society who's already done it, I think it'd be much nicer for us to share that person's project to get other people in the society engaged and giving it a go themselves. Yeah, it sounds to me like it's something they could do at home in lockdown as well.
Yeah, okay. I think it's not too hard to do, so I'd be more than happy. I'll share those files. Not a problem.
Wonderful. All right, Mark, the floor is yours to talk about the All Abilities project.
Okay, thank you, everyone. As you know, I'm Mark Justice. I'm the section director for the ASV's instrument making section, and I'm going to talk today a little bit about the ASV's All Abilities Astronomy Telescope. But first, I'm going to talk a little bit of history, so please bear with me before I get into the instrument making part of it. Just a moment, please. Sorry. Okay, all good. Yeah. So I'm going to talk a little bit about the history. When I joined the ASV back in the early 90s, the LMDS was a relatively simple affair. I mean, it had great skies and plenty of space, but there were sort of a tin shed club room / bit of a bunk room, and the toilets were sort of the place you only went to if you really had to. And I remember things like access was a bit difficult. I remember at one wet barbecue getting the Commodore a bit bogged on the way out and things like that. But it was a great place and people went there in numbers. But since then, the ASV has been working very effectively at ticking away at improving things at LMDSS. I mean, it's now got, proper track access. There's power on there now, which we never used to have. You've got, you know, piers and stuff around the astrophotography and observing fields to give you power. There's lots of other stuff, and I'll move on in a little bit. I mean, there's big telescopes have been added. We've got the radio telescope building, and now the dish itself, the Astrodome, the big 40-inch telescope. There's a whole lot of, you know, the fantastic bunk rooms and amenities building that's there. It's been really great, and it's I think all those improvements have made LMDSS far more accessible to members. It really has improved accessibility, and it's done great things for that. I'll just draw your attention in passing here. This is the 25-inch scope, and note the ladder there, a must-have accessory for both that scope and the 40-inch scope below it. So yeah, as I was saying before, there's been some fantastic improvements. Here's the Gym Trainer Observatory with the 40-inch scope in it. And as I say, they've made astronomy accessible to more and more people. However, as I mentioned, you need to be able to get around the site, which is sort of rough bush tracks and stuff, which you might feel uncomfortable with, and you've got to be able to climb ladders to look through these telescopes. I'm just going to digress for a moment for something that comes up in a moment. I just want you to draw attention to this point of this telescope, and this will come up in a moment. So if we raise and lower the telescope, this point stays fixed because it's the center of this radius, or this wheel that the telescope moves on. Anyway, I'll go back to the accessibility. So the ASV wants to make the accessibility even greater. So we're now looking at the All Abilities Astronomy project, which wants to bring, you know, astronomy to people who are perhaps in wheelchairs, physically disabled, uncomfortable climbing ladders, any, you know, young kids and all that sort of stuff. So we want to bring astronomy to more and more people. So there's three main things that are part of the All Abilities Astronomy project. We're putting sort of proper concrete or similar paths for access to the main areas around LMDSS. An electric gate has been fitted to the front of the property. This has already been done and replaces the farm gate. So easy in your car access for everyone, and it's great to control access to the site as well. And another big part of it, and the part I'm going to talk more about, is the All Abilities Astronomy project has a telescope and observatory component, and it's designed that this telescope and observatory can be used from a wheelchair or people in a wheelchair. But it's more than that. It's just people who don't want to climb ladders or are unable to, or small kids or whatever. If we just want to increase people we supply astronomy to. Note the observatory will have a roll-off roof, and it will have a little bit of a warm room at one end. It's been noted that quite often people with disabilities tend to feel the cold more and have problems regulating their body temperature. So we're trying to cover all bases, or as best as we can. I'd like to say that I believe, well, a suitable telescope, when I say a suitable telescope, something that we'll be modifying has already been purchased, and I believe the planning permit has been issued by Bendigo Council for the construction of the observatory and pathways. I'd like to also say at this point that a grant was received for the All Abilities Astronomy project, but certainly not all of the projects. So now there's been lots of ASV has to raise money for the remaining costs, and there's been some fantastic fundraising done. Mark Mascaro, and he's been working with a team of people, and some fantastic fundraising. And in fact, today, any money from the Galactic Center Star Party will go towards the All Abilities Astronomy project. So hats off to you there, Mark, and all your team and everyone else involved. So now I'm going to start talking about maybe more the instrument making part of things. was decided to, or it was chosen to modify an existing commercial telescope, and we chose a Hubble Optics 406mm or 16mm ultralight Dobsonian, and the actual beast is the one shown in this picture here. I'll point out that Hubble Optics made the mirror, just the mirror, for the Society's 40-inch telescope. The telescope itself was made by SDM. So this is the telescope we have. This is in its as-purchased Newtonian configuration. And you can see my cursor, can't you, Mark?
Yeah, yes, we can.
Yeah.
Yep,
Yeah,
absolutely.
okay. Yeah, so this is Newtonian. We have the primary mirror at the bottom here. We have the secondary mirror here and the focuser and eyepiece. So light comes in, reflects off the primary, converges onto the secondary mirror, bends at right angles and comes out here. So this telescope, this is a diagram of the actual telescope, and this eyepiece height is about sort of 1.8 meters. So, if you're reasonably tall, you can sort of look through the eyepiece at the zenith, but then it won't be at the zenith, but it's still got a fair bit of height to it. Again, the light comes in, reflects back, focusing through the secondary, bends at right angles and out to the eyepiece. So what we'd like to do is to try and get this viewing point lower. So you could, sort of put a flat mirror here and bend the light down again, but that doesn't get you far enough down. And if you move this mirror down any further, by the time you're down here, you've blocked most of the aperture. So what we do is we effectively put a negative mirror here, a bit like a Barlow, to extend the focal length. And that's the so-called Cassegrain arrangement that Barry talked about. So this mirror here, they call it the secondary mirror, the primary down here, secondary here. It's shaped like this. It's a convex mirror and it's hyperloidal, and that's arranged to correct the optics. So anyway, it brings it down here through a hole in the primary, and you can put your focuser here. But for something like a Dobsonian like we've got, to access the stuff immediately below the mirror here is quite difficult. So then we go one further and we use our original secondary, becomes our tertiary mirror, and it brings out light to the side here. And this, we arrange this point here to be effectively the center of the Dobsonian altitude bearings. You'll remember I pointed this point out in the 40-inch scope just a few slides ago. So this means as the telescope goes up and down, this height of this eyepiece and focuser here does not change. It'll obviously go round in a circle as you scan around in azimuth, but the height remains fixed. So what we're suggesting to do is we'll put this telescope up on a table, a very strong central column, a substantial platform on top, and this telescope will sit on top of it. And then you can have some dude here in a chair, or in fact, it provides great wheelchair access or seated access, or it's not quite a fixed eyepiece because it rotates around as the telescope rotates around, but it's quite easy to follow it, and it's always comfortably at that height and just looking straight ahead. This type of telescope arrangement is called a Nazmuth Telescope, and it was designed by invented by James Nazmuth. He was a Scottish engineer, and I like the guy. He retired at 48 to follow his astronomy interests. Sounds like a good deal to me. And after retiring, he then invented and built the Nazmuth Focus Telescope, and he's shown here seated at his telescope. His telescope is a little bit different. It's the same sort of thing. You sit here, but he actually has the whole floor rotates around, so he's sitting up on that chair. We contemplated that, but it's not that hard to follow the telescope around. Here again is the optical arrangement, sort of redrawn. Light comes in, reflects off primary, onto the hyperbolic secondary, back to the flat tertiary, and deflected out the side to the Nazmuth or Coudet focus. There's a couple of different names there. And if we didn't have that, we come out to the Cassegrain focus, which is a bit like all your Smith Cassegrains and that you've seen. These are pictures of the actual telescope. I just like to talk about some of the instrument making sort of interests of it. The mirror is a sandwich mirror. It's got two sheets of glass with these little buttons between them. I'll show you another edge-on view in a moment that'll get you a better feel for that. But it does make for a very light and very stiff structure that cools very quickly. I'll talk a bit more in a moment. And the support is actually quite a simple 6-point support. So we have these pivoting arms that are supported here, 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 and then there's a pair underneath here. These wires are just to stop these rotating out of the way. So it's quite a simple support. I like the way that it's a bit hard to see, but these are the 3 collimation screws, and they don't act upon these 3 points, but on a frame. So the frame that you can see here, here, and here, the frame supports the 3 support arms, and the frame also supports the sling that goes around the mirror. So you can get the sling and the arms and everything in the perfect position, and then you're not sort of affecting that when you twiddle with the collimation screws. It's not sort of moving the mirror forward or backwards on the sling. All this construction here is welded aluminium, powder coated, quite nicely made, very functional. Here's an edge view of the mirror. So it's probably about 42 millimeters thick, and it's got like a 16 millimeter plate top and bottom, and you can see these little buttons in here. They've been positioned between the 2 plates, and then the whole assembly has been heated up and fused together. Now this makes something that's quite stiff, certainly for its weight. It gives great stiffness for the weight, but more importantly, it provides something that cools incredibly well. I mean, normally, if you had a normal mirror, this might be, 50 mil thick, 60 mil, 70 mil, or something like that. And it means the glass in the middle of your mirror never really cools. And you have to remember that you've got this aluminium coating on top, which actually stops the mirror cooling in this area. So in the case of this sandwich mirror, any heat along the surface here can get out on this surface and be vented out through the gap. So they cool very well. I mean, there's talk about as the mirrors cool down, they change shape and all that sort of stuff, which is true, but as much of the problem with anything is hot air just on the surface of the mirror changing the refractive index of the air around there and causing aberrations in the wavefront and stuff. So we need to get this surface of the glass the same as the air temperature, and this sort of arrangement does a great job. I'm just going to back up a minute because I forgot to say something. This arrangement here, Barry Adcock has been working with this, and he's the expert on this sort of things. So this is a commercial mirror. It's a commercial, was the secondary, is now been brought into play as the tertiary, and Barry has designed the various distances here, and he is currently making this mirror. He's already ground it to shape, and I believe he has been polishing the back and will be polishing the surface proper reasonably soon. He'll also be making this assembly here, and then there'll be other assemblies made to support the focuser out here, and there'll also be an assembly to support the tertiary. The machining for this and the manufacture of these items, and maybe some of the above, will be looked after by Sidereal Trading and Paul Litchin, and Diego will be working with that. Just wanted to give there. Okay, there's only a couple of pictures to go, and I just wanted to. I put this together. This is a wheelchair I got. This is my son sitting in the chair. He's not at all wheelchair bound or anything. And this is the telescope itself with a bit of a mock-up holding where the eyepiece will go. This is on my dining room table. I just wanted to get a feel and show people how it'll work. So it'll be set up something like this. I did talk about the support for the telescope. So then that telescope's pointing here, you rotate it around to this view, but it's actually exactly the same eyepiece height. You just have to follow it around. And then if you lower the telescope down, again, it's the same eyepiece height. Note this setup here, this mock-up, we don't have the secondary mounted up here yet, and also the tertiary is not mounted here. I'll draw your attention to the hole in the primary here. And we're actually going to mount the tertiary mirror here with a support structure through that hole mounted to the back of the frame of the telescope. We're doing that so as to not introduce another set of spider veins and resultant diffraction. And as Barry pointed on about earlier, the less obstruction you have, the better off you are, and that includes spider veins or additional sets because they'll never line up quite properly. And that's all I've got to say at present. It's currently that the secondary is being made, and it will go in the quite near future, probably to get the other parts for supporting the eyepiece and the tertiary made up. So anyway, thank you everyone.
So we've got a couple of questions for you. Neil he's made a note of collimating the tertiary is going to be tricky with the primary so close behind it. So is that something you've considered?
Yeah, there's a couple of ways of collimating it. You can collimate it with screws that are in front of the primary, or you can collimate it by collimating the tube that goes through the center of the primary. So you may in fact be collimating the tertiary with screws from behind the primary. So it's actually not that close either. It's probably 350 millimeters above the primary, so there's still room. It's really not too bad. It's easy to access. I suppose you just have to be a bit careful you don't, I don't know, drag your hands across the primary, but I don't see it being as a big problem. No, it hasn't been decided whether collimation will be on the tertiary assembly or behind. Any others, Mark?
Yes, so Lee, is there a need or provision for passing air through the sandwich structure of the mirror to maintain an even temperature?
The suggestion is it's not necessary with this small, as in 16-inch telescope, and any natural convection and stuff. They do not recommend fans. They do not fit fans to them. It's a very open structure. The edges, well, they do not recommend fans. They say they are not necessary. So at present, we're relying on the recommendations of the manufacturer, but they very carefully state no fans required. It's thin enough plates. They'll cool down remarkably quickly without that. So
I've got one more for you. Alan, absolutely love the concept and appreciate all the effort everyone's putting in. Just wondering if there is any way we could alter the viewing height to suit the viewer. So have we considered that some people are going to be sitting lower in a wheelchair, being older or younger?
Yeah, there has been some discussion, and at present, the concept of mounting it on a table is there, or a support. There's still open to discussion a bit. If we can arrange some height adjustment, I think it would be good. Do people? I'm after some feedback here. Do people think it's necessary to adjust the height?
I would think it probably would be when you think about it. So if you've got young children sitting down or looking through it, and then you've got someone, so people's eye height is going to be at a different level depending on how tall they are sitting down. So I think it might be something we should consider.
I mean, it's not.
Just gave you more work, but
but it's not sort of. It's quite feasible, very plausible, very plausible. I'll just invite Barry. Barry, you're doing all the optics and the optical layout and design for this. Do you have anything to add, Barry? Have I missed something or?
No, I think you've covered it very well, Mark.
Oh, thank you.
I was just pondering this different height problem. I've always imagined, or I've always thought that on the ground we'll have a couple of pellets with sort of a roll-on ramp, and if we have 2 or 3 of those of various heights, I think we could cover a lot of situations, from children to elderly people who want to sit down. And I mean, even if you are sitting down, or even if you're disabled, you are able to move your head vertically a little bit. So just a couple of perhaps pellets with a roll-on ramp of a couple of different heights will cater for what we've been talking about.
Yeah. So John's pointing out that providing a chair with height adjustment is an option, but I don't think it is, because I think the idea of this is that if you're going to have people who are in wheelchairs, they're not going to be able to be moved from the wheelchair to the height adjustable chair. The idea is to be able to wheel that person up in their own chair to view through the eyepiece. That would work for children and things like that, to have an adjustable chair on site for them to use.
Yeah, I do imagine there will be an office chair or 2 in there, because you don't have to be in a wheelchair to be using this telescope. I mean, there will be chairs, and kids will love it, and I'll probably love it because I don't have to climb the ladder in the dark, and just sitting on an office chair observing sounds fantastic. But yeah, we will think a bit more about that height for wheelchair people. Any other comments, Barry? Or
no, I think you've covered it very well, Mark. Very well.
Okay, thank you. Any more questions on anything? No. Any of the presentations tonight? We're pushing our time a bit, aren't we, Mark?
Yeah, I'm hungry. No.
Yeah.
No, I've got 3 hours till the next one. So.
Okay. Well, I'm going to say thank you very much to those who agreed to present. Great effort, fantastically done. Thank you. I look forward to catching up with all you guys at the next instrument making section, which is going to be by Zoom. And I encourage any viewers to join in. You don't need an invite. Just pick up the Zoom link off the ASV webpage, members, Zoom links, grab it. We tend to start at about 2:30, any formal presentations, run through them, and then it's a little bit of a chat at the end. We go for about an hour and a half when we're on Zoom. Okay, I'm reading about Robert there. Fantastic, so Robert. I look forward to
Robert's an ASV member, so this is he's one of the reasons why we're doing this, so that Robert can come up to the site and have a look through a telescope.
I'm keen on any feedback or suggestions, Robert. Or I mean, I'm not limited mobility, so us guys like that probably overlook the obvious. So please, anything you think of, or if you see we're going in the wrong direction, please tell us. We'd appreciate it. Yeah.
All right. Well, thank you everyone for joining us this afternoon. We hope you learned something interesting about instrument making. I know I did. I really like Barry's dumpster telescope. That one's pretty cool. That was probably my favourite of all of them. And I'd like to thank Mark, Rod, Barry, Stuart and Jim for sharing their knowledge today. And as Mark noted, this weekend's live streams are all about raising money for the All Abilities Astronomy Project, which will give so many people a pathway to the planets, an opportunity to see the stars. So don't forget to grab your raffle tickets. The link's on our Facebook page and website. It will be closing at about 8 o'clock, so we can get it all together and ready for the draw at 9 o'clock. So if you haven't got one, or if you want to grab some more, grab them now, because come 8 o'clock you won't be able to grab them anymore. And we'll see you at 9 o'clock for our Deep Sky live stream session.
But thank you, Mark.
I know it's cloudy outside at the moment in Melbourne, but we have got we have got people around Victoria, and we've got someone in Queensland where they have clear skies. So we will be able to bring live stacked deep sky objects tonight. So we'll see you at 9 o'clock.
Thank you, Mark. Thanks for your efforts. Fantastic.
Thank you both.